30 minutos? Sim?
Boa tarde a todos. Hoje a gente tem o prazer de receber aqui a doutora Ciria Lima Dias. Muito obrigada por aceitar o nosso convite. A doutora Ciria Lima Dias é uma astrônoma brasileira que tem focado em evolução galáctica, em ambientes densos. Ela obteve o seu bacharelado em Física na Universidade Estadual de Feira de Santana, um mestrado em Astrofísica e Física Computacional na Universidade Cruzeiro do Sul e completou o seu doutorado em Astronomia na Universidade de La Serena. Atualmente, ela tem estudado transformações estruturais e o quenching de formação estelar em aglomerados de galáxias próximas, tais como, por exemplo, Hydra e Antlia, juntamente em colaboração com o S Plus e o Chances. Muito obrigada.
Obrigada,
o tempo
Angela.
é todo seu.
Eu que agradeço de estar aqui. I have to shift it to English. I'm so sorry. Yes. Thank you, Angela, very much. As Angela told you, I'm working with galaxy evolution dense environments. I'm looking at physical and the morphological properties of galaxies, but I mainly work with nearby cluster. This research I'm doing in collaboration with Professor Antonella Monachesi and Sérgio Torres Flores, that are professors at Universidad of La Serena in Chile. And I'm also working with Giselle Montegu, that's a postdoc here, but was a student in La Serena with me. And why I want to study evolution of galaxies in dense environments. I really like this illustration because it's related about a lot of phenomena that can affect the evolution of galaxy. For example, when a galaxy evolves isolated, we have some secular evolution process that can change the galaxy. However, when a galaxy is inside a dense environment, there are other phenomena that can change the galaxy. And when I'm talking about morphological and physical properties, I know that morphological is also physical properties, but when I'm talking about morphology, I'm talking about the shape of the galaxy. When I'm talking about physical properties, it's the star formation, the stellar mass, the metallicity, the gas content, all those properties of the galaxy. And for example, if a galaxy is inside a cluster of galaxy, for example, we have, I don't know if you can see very well, there are so many phenomena like the Hahn pressure stripping, that is when a galaxy falls in the cluster, the galaxy can lose the gas that is necessary to form a star, and the galaxy can stop the star formation. If the galaxy is not in a so dense environment like a cluster, in a group of galaxies, we can have more galaxy encounters that can change, of course, the morphology, and sometimes could increase the star formation, not stop the star formation. We have starvation that, for example, if there are some filaments or some channels that is filling the galaxy with gas that is necessary to form a star, if the galaxy is inside the cluster, the galaxy stop to receive gas and we stop the star formation. I will not talk about all those properties, but all these can happen inside a dense environment. And all these will impact different galaxy, the morphology and the physical properties. So, as I told, I want to look at how the galaxy evolve in a dense environment. So the first thing that we have to do is to classify. And I always say that it's not only about galaxies. If we work with stars, we need to classify. If I work with plants, I need to classify the plants. So there are so many ways to classify the morphology of galaxy. We can do visual inspection if you have a few galaxies. We have, for example, Hubble type, the Vukule class. We have so many ways to classify the morphology of the galaxy. But in general, a simple way that we can do is try to separate galaxies by early type galaxy and the late type galaxy. So I know that I'm talking about a lot of things that a lot of people knows, but I have to say anyway. Early type galaxies in general are elliptical galaxies, lenticular galaxies, S0 galaxies, and the shape of galaxies also related with some physical properties. So when I'm talking about early type galaxies, we expect to see like elliptical, red, quenched galaxy with no little star formation. And when we talk about late type galaxy, we expect to see like a disc type galaxy with arms or bars, or irregular galaxy with a blue color and with a higher star formation rate. So we need to choose the classification that is interesting for the type of science that we want to do. In my case, that I want to see how different type of galaxies are inside the cluster, I just choose to separate galaxy by early type galaxy and late type galaxy. I will talk more later. And why I'm doing this, the question is, does the environment affect the morphology of galaxy? Yes. There are so many works that you look at the type of galaxy related with the environment. For example, this is the classical work of Dressler that look at the fraction of different type of galaxy with local density. And Dressler found that higher is the local density, higher is the fraction of early type galaxy, like elliptical and S0 galaxy. And the higher is the local density, and lower is the fraction of spiral galaxy and the irregular galaxy. This was found really early. However, there are some discussion in the literature, for example, Fasano, this paper here, also look at the fraction of different type of galaxies related to the local density, and find a similar result as Dressler. Like higher is local density, higher is the fraction of early type galaxy here in red, and the lower is the fraction of spiral galaxy. However, Fasano didn't find a relation between lenticular galaxy, S0 galaxy, as Dressler found. This work is really nice. This work is from Leo 2020. And what Leo did was look at the same idea, the fraction of early type galaxy, look at the morphological property like early type and late type galaxy, and also physical properties like quenching galaxy and the main sequence galaxy, star-forming galaxy, and look at how the fraction of this type of galaxies change with the environment. So really low dense environment like voids, sheets, filaments, and cluster, and found a similar result. Like higher is the environment, like cluster, higher is the fraction of quantity and the early type galaxy. But what is interesting that Leo found is that, as you can see, the fraction of quantity galaxy is higher than the fraction of early type galaxy. And this means that the galaxy stop the star formation and after that change the morphology. So the galaxy probably go inside the cluster, the hum pressure stripping, starvation, evaporation, all this phenomenon remove the gas of the galaxy. So the galaxy stop the star formation and after that change the morphology. I will not talk about all the works, but there are so many works. This is a classical work from, those are classical works, but this is a recent work from Paulo, from Rio, that also look at the fraction of different type of galaxy morphology as well, and found that even up 5 at 200 of the cluster, even at high distance from the center of the cluster, there are some influence of the cluster in the morphology and the physical properties. And we can see that the fraction of star-forming galaxy is lower than the fraction, for a galaxy that inside the cluster and belongs to the cluster, comparing with the field fraction of star-forming galaxy. And this here, it's a work from Giselle that was published this year. Giselle is work with compact groups. Giselle work with dense environment as well, with compact groups. And Giselle look at, for example, compact groups that are isolated and compact groups that are inside a higher dense environment. And they found that there is some influence of the dense environment in the galaxy of compact group as well. Talk about this, the environment, because there are so many works, but there are some open questions as well. And almost all the work that was done looking at the properties of galaxies are in the central part of the clusters. Like mainly all the works are inside 1 at 200 or the visualized area of the cluster, up 2 at 200 of the cluster, but a few works go up to 5 at 200. So, and we want to look at the preprocessing because as I showed you before, this work from Paulo, we can see there is some influence of the environment, the cluster, the galaxy cluster, up to 5 at 200. So we need to look at this to see the preprocessing, to see, for example, how many galaxies it's falling in the cluster already quantified or like with a early type morphology. And because of this, that it's coming a survey called Chances, Chilean Cluster Galaxy Evolution Survey, that we will observe more or less 150 clusters from the nearby universe like Fornax, Antlia, and Hydra to up to 0.45 in redshift, and we'll have spectral data for all those clusters, more or less 150 clusters, up to 5 R200. So we will be able to look at the pre-processing as never was done before, I mean, with a massive quantity of data and with spectroscopy data. And all those clusters are covered by legacy data, decals data. So we will have images for the galaxies, and we will have the spectra of the galaxy. So we'll be able to look at the morphology and physical properties. And these, we have a higher synergy with S+. Mainly my work, I'm using S+ data at the moment. This is the distribution of cluster that will be observed in the south hemisphere mainly. All the clusters that are like in green color, we have S+ data. We use the S+ data to select the targets. I was in a position before this postdoc that I'm doing now, my work was just to select the targets that will be observed by chances. And we used S+ photos that Eric determined to select the candidates to be observed. And in green are S+ data, and in, what's the color? Magenta? In magenta, it's also S+ data, but it was by like internal data, like the people asked time to get this data, this photometry. There are some clusters that we don't have S+ data, but mainly, indeed, Olorogeon, Shapley, supercluster, Antlia, Hydra, all we have S+ data. Indeed, Antlia is the only cluster that will be observed by chances that we don't have decam data. We are using only S+ data to select the targets and to look at the morphology, the image of the galaxy. I have to learn how to use this. So, about the research, what I'm doing. As Angela told you, I'm interested in the nearby cluster. And why? Because I can see the galaxy very well resolved. I can see the morphology of the galaxy. I can model the light profile of the galaxy with a good precision and get information, structural information of the galaxy. So one of the really nearby cluster, it's the Hydra cluster. This is the central part of the cluster. Hydra don't have a central BCG, has these two BCGs here, and a huge spiral galaxy that I don't know how this galaxy survive inside this environment, but it's a galaxy with the redshift of the cluster. This is just information about the cluster with a mass 3.1, 10 to 14 solar masses. Hydra have a lower mass, Hydra has a higher mass than Antlia, that I'll talk more later. And the Hydra looks like it's a relaxed cluster. The X-ray distribution of the cluster is really smooth, looks like a relaxed cluster. So what we did, what we did, because as I said, I'm working with Giselle and the other people. We are using S+ data. I will not talk about our of S+. I think that almost everybody knows S+. There are anyone that don't know S+? Everybody knows S+? I think so. Okay. So S+, the telescope is in Chile. We have 12 bands, and we can model the galaxy in the 12 bands and get structural information about the galaxy in these 12 bands. So I talk about classification. We can do visual inspection, but we will do this if we have few galaxies. When we have a lot of data, we have to choose other ways. For example, I know that the group of Angela work with no parametrical information of galaxy to classify galaxy. This is interesting because we don't have like a prior for the galaxy. We just have need the image, and we can determine some asymmetry, smoothness, concentration, and use those parameters to separate different type of galaxies or candidates to Hahn pressure stripping, all those things. In my case, I'm using parametrical way to classify galaxy. I will say this way. I model the galaxy with a Sérsic profile that I will talk more about later. And when we model the galaxy with a Sérsic profile, we can get magnitudes, effective radius, Sérsic index, a lot of information that we can use to separate different type of galaxies. For example, here is the Sérsic index. That the Sérsic index gives us information about how concentrated is the light of the galaxy. And we can use like the color and the Sérsic index, as you can see. This is not workable. So we can see that in general, different type of galaxies L-type galaxy occupy this zone and the late-type galaxy occupy this zone. We can use the ratio between the different Sérsic index in different bands. You can see that if you use this, you can concentrate very well. I don't know, this is not working. We can concentrate very well the L-type galaxy in this part of the plot. So basically, we're using this to classify galaxies. As I said, this is the equation from the Sérsic profile. This is the Sérsic index, as I told you. It's related how concentrated is the light of the galaxy. This is how this profile behaves related to the Sérsic index. So, in general, L-type galaxy, elliptical galaxy, S0 not so much, but elliptical galaxy and the S0 galaxy that have a pronunciate bulge have a higher Sérsic index because you have a high intensity in the central part of the cluster. So we can see the behavior of this profile here. And when we have like late-type galaxy with a disk, we have a profile that's not so concentrated. Like it's indeed a disk profile. It's equal 1, the Sérsic index. Sorry, it's not coming. But okay, a disk profile, it's Sérsic index equal 1, and if you have a bar, the Sérsic index in general is lower than 1, for example, because we can model the galaxy with one profile, but we can put the quantity of profiles that we need to model the galaxy, the quantity of components that the galaxy have. So we can use this to separate L-type from late-type galaxy, L-type from late-type galaxies. So what I did, as I told you, we can model the galaxy just with one component. Sorry, we can model the galaxy just with one component, but one thing that we can do as well is separate the bulge and the disk of the galaxy, because in general, galaxy has more than two components, not only a bulge and a bar and a disk, but in general, we can model the galaxy like with a bulge and a disk to get the information from the two components of the galaxy, and it can help us to classify as well. So this is one example of a galaxy with S plus data. In the top part, we can see the S plus data. This is the model that is an ideal model, and this is the residual that we get after subtract the model by the real image. As you can see here, I really like this band from S plus, that is the H alpha band. We can see that this galaxy has a bulge, a bar, arms. I don't know if you can see, but there are some star-forming region in this galaxy as well. So this is a beautiful galaxy that we can see in the 12 bands, because there are some galaxies. The people that work with S plus know there are some galaxies that we can see, like in the red bands, but we cannot see in the blue bands. But this galaxy we can see in all bands. And with this, as I told you, we can get the Sérsic index, the magnitudes, the bit of array to try to classify the shape of the morphology, the positioning of the galaxy, that we can try to relate the positioning with the general environment as well. I think that Leah is working with that, look at the positioning of the galaxy related to the environment. So with this, the first thing that we did was try to see if we model galaxy with S plus data, if you can separate the galaxy by L-type and late-type galaxy using the Sérsic index and the color. And this is distribution of galaxies inside 1 to 200 of the Hydra cluster. And we can see, as we expected, almost all the galaxies are in the L-type zone. We are talking about a cluster. We expected inside almost virialized cluster, because we saw that the X-ray map, it's like smooth, looks like a virialized cluster. So we have a higher fraction of L-type galaxy compared to late-type galaxy. This region here, it's the region that Giselle really liked to work with, the transition galaxy. I have a few here, but the transition galaxies are galaxies that, as you can see, have a low Sérsic index. So those galaxies has like a disk shape. The morphology looks like a late-type galaxy, however, have a red color. So those galaxies probably are starting to change the morphology, as I told before. The idea is that the galaxy stop the star formation, and after that, they change the morphology. So those galaxies has yet like the disk morphology, but probably stop the star formation already. And one thing that's interesting for S plus, in our case, that we have a huge area in the sky, is that we have the H alpha band. that only for nearby cluster like Hydra, Fornax, and Antlia, we can use the H-alpha band to get like a prox to see if the galaxy is a star-forming galaxy or a quenching galaxy. Of course, it's not so precise as like spectroscopy, but we in general, I applied the tree filtering method to see the galaxies that are star-forming, and we found very well that there are some late type galaxies that are star-forming galaxy. So we can use S plus data to do this type of analysis. This was a study that we did only in the central region. The idea is to expand for all the clusters that Antlia, Giselle, a lot of people here is doing that. Just to talk about, we can see that there is a relation between stellar mass and Sérsic index. Higher the stellar mass of the galaxy, higher the Sérsic index, the galaxy is more concentrated. So one thing that we look at as well, I told you, the X-ray map, it's smooth, looks like helixed cluster. This is the information in the literature. But we apply a Dressler-Sheckman test to see if Hydra is a helixed cluster or not. This is the central region of the cluster. As I told you, we apply the Dressler-Sheckman test. This is the delta for the Dressler-Sheckman test. Higher is the delta for each galaxy. Higher is the probability the galaxy belong to a substructure. The Dressler-Sheckman test don't assign a galaxy to a substructure, however, give like a clue that probably the galaxy belongs to a substructure. So in this plot, higher is the circle, higher is the probability of the galaxy be in a substructure in a group. So we can see here that we found like galaxy here that it is in a substructure inside, really close to the central part of the galaxy, and like in falling region, let me say this way. So what we did was apply a DBS scan. There is a code called the 8 dBs scan, but we use also a DBS scan that use information about the position of the galaxy in the sky to assign if the galaxy belongs to a substructure. What is interesting is that this substructure here, specifically, we can find using Dressler-Sheckman test, and we can find the same one using the DBS scan. And I will talk more about this later. Sorry? Okay, thank you very much. As I told you, the Dressler-Sheckman test don't assign a galaxy to a substructure. Just give an idea that probably belong to a one. But if we do the distribution of all the deltas for all the galaxy, if a galaxy have like a delta that is 3 times the sigma of the distribution, probably the galaxy belongs to a substructure. And those square are galaxies with a really high delta, so probably belong to a substructure. And the are those ones that we are seeing with the square. As you can see, it have a higher circle. And what we look as well, because I was talking about in the beginning of the talk about pre-processing. Probably when a galaxy falls inside a cluster in a group, in general, the environment of the group, as Giselle found in her work, probably the interaction between the galaxies inside the group can stop the star formation until the morphology of galaxy. And what we look at was, for example, here, in this plot here, this is the same plot that in the last slide, but this is the delta. So high is the delta, probably those galaxies are in substructure with the square, and the objects that are with stars are star-forming galaxies. In general, star-forming galaxies are in regions that have a low probability to belong to a substructure, are really region with a low density. Those are the locations that we find the star-forming galaxy in Hydra. However, we can see there are some star-forming galaxies in high region of substructure. Probably it's exactly the same group here. This group have some star-forming galaxy that they are these 2 star-forming galaxies here, and sometimes the interaction of galaxy also can increase the probability to the galaxy form star. And this will be really quick, like the interaction of the galaxy will trigger the star formation and the galaxy will stop the star formation, mainly because it's inside the cluster. But in general, the conclusion is we find galaxies that are star forming mainly in region with low delta, with low probability to belong to a substructure. And also, we look at this in the phase space diagram. The phase space diagram, this is the distance from the center of the cluster. This is the distance for the center of the cluster in the central region. And this is the peculiar velocity of the galaxy with respect to the recessional velocity of the cluster divided by the dispersion velocity of the cluster. And these are the same plots. The difference is that galaxies here are color-coded by the Sérsic index. And again, the circle, it's proportional to the delta from the Dirac-Schekman test. As you can see, this group of galaxies here are the group of galaxies that is following the cluster, that there are some, as you can see here in this plot, the galaxies are color-coded by the specific star formation rate. All those galaxies are star-forming galaxies. And this is the only group that is following the cluster that still have some star formation. This happened with the Hydra cluster. We'll talk about the Antlia cluster. It's really different. Antlia cluster have a lot of more substructure compared to the Hydra cluster. But in the conclusion of this, let me come back. The conclusion of this from the Dirac-Schekman test is that Hydra, it's close to be realized, but it's not there yet. There are some substructure in Hydra, in the central region of the cluster, but it's almost there. So another thing that we tried to investigate was the mass-size relation of the galaxy inside the cluster. The mass, it's a really important property of the galaxy. If the galaxy is isolated with a circular evolution, the mass is really important. But if the galaxy is inside the dense environment, it's important as well. In general, we have like a quenching process that's related with the mass of the galaxy as well. So, and why I want to investigate the mass-size relation, because, for example, higher is the mass of the galaxy, higher is the size of the galaxy. It is what we expected. However, the position of the galaxy in the mass-size relation, it's also related with the evolution of those galaxies. In general, galaxies that grow the mass by star formation occupy this zone in the mass-size relation, and the galaxies that grow the mass by measure occupy this zone here, the mass-size relation. There are other properties as well. Here, for example, galaxies that are fast rotator or slow rotator, disk-type galaxy in general are above of elliptical galaxy. So the position of the galaxy in the mass-size relation, it's related with the secular evolution, the process that the galaxy passed to evolve and the growth and mass. So, So we look at the mass-size relation of the Hydra cluster. What we found, what we expect. Higher is the mass of the galaxy, high is the size of the galaxy. This is what we expect. But I want to look at the color, and I will try to create like a scenario, because the galaxies here are color-coded by the bulge total flux. So it's the flux of the bulge divided by the total flux of the galaxy. So bulge-dominated galaxy have a higher value, like higher than 0.5. So bulge-dominated galaxy are the, I don't know, pink, magenta one. And the disk-dominated galaxy are the yellow one. This is the same plot. And here, as you can see, the galaxies are color-coded by the color of the galaxy. The color of the galaxy is related with the star formation. So in general, Hydra galaxy occupy this zone. If you look at like a specific stellar mass, if you look at a fixed stellar mass, in general, the red galaxy are below of the blue, dark blue galaxy that are below the, I don't know, light blue galaxy. We have a few points. We need to do this with more galaxy. But what is interesting, as you can see, the bulge-dominated galaxy, when we look at the fixed stellar mass, have a lower size compared to the disk galaxy. And what we believe is that the galaxy fall inside the cluster, probably the hum pressure steeping, some harassment, some process inside the cluster, make the galaxy loose like the gas. Sometimes the galaxy can lose even stars, start to be bulge-dominated and start to be like smaller. And of course, if the galaxy lose gas, the galaxy also will stop the star formation. And because of that, the galaxy start to be like with a red color. And this is the scenario that is happening inside the cluster. This is a really interesting result that we found. And another thing that we look at was the mass-size relation from the bulge and the disk. So this here is the size of, the mass of the galaxy, and this is the size of the bulge. The circle ones are the bulge, the size of the bulge, and the triangles are the size of the disk. And when I was doing this plot, I was expecting to see high is the mass of the galaxy, high is the size of the bulge, and the higher is the mass of the galaxy, higher is the size of the disk. But as you can see, there is no relation between the mass of the galaxy and the size of the bulge. It's like whatever the mass of the galaxy, the bulge can have the size that the bulge wants. Like there is no relation between the size of the bulge and the mass of the galaxy. However, there is a relation between the disk size and the mass of the galaxy. So what we conclude is that probably the general behavior that we see, the whole size of the galaxy with the mass of the galaxies are driven by like the disk. It's disk that is responsible for general mass size relation that we found. And indeed, I did the same plot with the absolute magnitude just to see if the mass, we know that is related the absolute magnitude of the mass of the galaxy, and we didn't find any relation between the size of the bulge. We published this paper. I didn't like this result because I was really expecting to see a relation between the size of the bulge and the mass of the galaxy, but we published this anyway because this was what we found. But after we published this paper, there are more papers that found the same relation. Like there are more papers that found also there is no relation between the size of the bulge. I don't know why, but there is no relation between the size of the bulge. There is an exception for the people that work with really high mass galaxy. It's like there is, if we are working this regime here that I'm not in work with, there is like a trend to increase this way. But I have to find galaxy with this mass inside the cluster to see. And it was for field galaxy. Everything that I talked before was about the Hydra cluster, and now I will talk about the Antlia cluster. As I said, we have 3 nearby clusters that we can see the galaxy very well, and we can model, we can resolve the properties of the galaxy. Antlia, it's closer than the Hydra cluster. Antlia don't have like I mean, there are some discussion in the literature if the Antlia cluster has a BCG or not. Every time that I talk about Antlia, Laerte say, I talk about, the Antlia cluster, Laerte start. I don't know if it's a cluster, maybe it's just 2 groups, because we don't know. In general, Antlia we classify like a cluster, but we have these 2 groups of galaxies that are interacting. Clearly, it's not a relaxed cluster. There are a lot of interaction, a lot of substructure inside the cluster. And because of that, I want to investigate this cluster. Indeed, to compare with the Hydra cluster, because the 2 clusters, it's close in redshift and it's close in physical space in the sky. And my last work, what I did, as I told before, I was selecting the targets that will be observed by chances. So I used S plus data, not the photo Z. In general, we use the photo Z of S plus to select the targets that will be observed by chances. But in the case of Antlia, it's so nearby that the uncertainty of the photo Z is the distance from the cluster that I decided not to use. I know that Eric and Claudia is doing some tests, and it looks like we can use the photo Z in the redshift of Antlia, but I didn't use. What we did, we look at the sky, all the spectroscopic information, and selected the spec Z members of a galaxy with information of spectroscopy. We look at the distribution of the galaxies that are those in blue here, and we fit a head sequence of those galaxies, and we selected all objects that are like in the head sequence. Those blue are spec Z members. We have a spectroscopic information and belongs to the cluster and the following regions. We fit the head sequence and select everything that are like 2 sigma above the head sequence and everything that's blue below the head sequence. I know that we have a lot of contamination. I know that we have foreground and background objects, but these will be observed by chances, and we will have the spectroscopy for those galaxies, and then we will select the galaxies that belong to the cluster. So just for fun, we start to look at the properties of those galaxies that we have spec Z information. So we know that belong to the cluster. Let's see the distribution of those galaxies. This is the same idea, the color of the galaxy and the Sérsic index in the R band. We can see, I don't know if you remember the plot of Hydra, we have so many objects here, but now we have more objects in the late type zone. Why? because now we're looking up to 5R200. And for Hydra, the work that we did was just in the central part of the cluster. So we have a lot of late type galaxy, and the galaxy here are color-coded by the star-forming and the quenched state of the galaxy. So as we expected, in general, star-forming galaxy occupy the late type zone, and quenched galaxy in general occupy the early type zone. And we start to look at the distribution of those galaxies related to the distance from the center of the cluster and the local density that I'll talk more later. The problem that we have here is that we are not completing the sample. We know, as I showed you before, that we have like a lot of objects in the central part, but we are not completing the sample. The idea is that when we have chances data, we will have spectroscopy for all those objects, and they will be completing the sample. But now we will look at the properties for the galaxy that we have information. So the central part of the cluster inside 1R200 that were complete, we can see very well that the cluster behave as we expected. We have a higher fraction of quenched galaxy than star-forming galaxy, but up to 5R200, the cluster is dominated by star-forming galaxy. Indeed, when I did this plot, I was thinking, also, something's wrong. Maybe I classify star-forming quenched galaxy wrong, but when I look at the galaxy, all the galaxies are star-forming galaxy. Indeed, I think that maybe the spectroscopy information that we have, I used the data that Eric compiled for the South Hemisphere. I asked Eric, there are some bias for star-forming galaxy in the data. Eric told me that there is no bias for star-forming galaxy, but I think that the information of the SPECSI members come from different surveys. We don't have SDSS data in the Antlia area. We don't have DECAN data, DESI data. So come from few surveys or few works, it's not homogeneous. But when I look at the galaxy, all the galaxies are really star-forming galaxy, beautiful galaxy, huge galaxy with arms, a bar, a star-forming region. So the cluster is dominated by star-forming galaxy. Indeed, there are some works, not one, some works in the Antlia area that just look at H1 emission. There are so many H1 data, galaxy with H1 emission in the area of Antlia. Other thing that we look, as I told before, was looking the substructure in the cluster to see if the different type galaxy how those objects are related to the substructure. I will not read the table, don't worry. But the blue points are galaxies that belong to the cluster, and they are in 4 regions of the cluster. And the galaxies with color are some substructure that was detected inside the cluster. And I was doing this to look at, okay, what's the fraction of quenched galaxy or star-forming galaxy related to the substructure? Because when I'm talking about substructure, we can say as well that it could be just a group of galaxies that's falling in the cluster. And in general, we expect it to happen some pre-processing. I told before that sometimes the interaction of galaxy can trigger the star formation, but in general, stop the star formation. And what we found is that even with a sample that are not completed, we can see here from this table, we just submitted the paper, but we have to, I didn't put in the archive yet, but we can see that the fraction of quenched galaxy, when we compare the substructure, the fraction of quenched galaxy is higher than the fraction of quenched galaxy for galaxies that belong to the cluster, but are not associated with any substructure. So probably there are some pre-processing inside groups that are stopping the star formation, that galaxies that are falling isolated, I mean, it's falling inside the cluster, but they are not in a group, can continue forming star longer than galaxies that are in substructure inside the cluster. This is the local density. I just show you some plots that I showed before for Hydra, but just for consistency and to see if with the data that we have, we can reproduce what we expect to see. So this is the local density of the cluster, and you can see that higher is the local density, higher is the fraction of quenched galaxy, and the lower is the fraction of star-forming galaxy as we expected. And the fraction of early type and late type galaxy, in general, early type galaxy is higher, but we have the bar, the uncertainty is really high. So it's basically the same fraction related to the local density. that is the central part of the cluster dominated this, of course. And these basically are my last slides, because I showed you before the phase space diagram from the Hydra cluster. This is the same idea, but I used another phase space diagram that is separated by zones. These zones are related. This zone was created with simulation. RE 2070 used simulation of galaxy cluster, and look at how, for example, early in folly galaxy, what's the zone that this type of galaxy occupy in the phase space diagram? Like background and foreground galaxy, what the zone that this type of galaxy occupy. So these zones indicate when the galaxy falls in the cluster. So the central zone here, it's the galaxies that basically are in the virialized zone of the cluster, was early in folly. Those galaxies that are in this zone here already passed to the cluster one time and are come back to the cluster. So this is interesting. What we can see in general, I will not talk about each specific zone, but again, the galaxies here are separated by star forming quenching, so physical property, morphology, late type, and the early type zone. I don't know if you can see, but in general, quenching galaxy occupy this zone. And star forming galaxy, these are really, I prefer this here because a density map is the same plot, but here I put a density map that we can see here that the quenching galaxy in general occupy this zone. The early falling, the galaxies that pass to the cluster at least one time, and this zone here supposed to be galaxies that are not bounded to the cluster, and this we have a mix of population. So quenching galaxies occupy mainly here, and I don't know if you can see there is a little density here. One thing that's important to say that I didn't told before, so Hydra and the Antlia cluster are nearby are close in redshift and physical space. So 5 at 200, that it's what I'm looking here, 5 at 200 of the cluster of Antlia, it's almost in the central part of Hydra. So there is some influence of Hydra here in this zone. And here is the density map that I don't know if you can see for a star forming galaxy. And this is the zone that we have a higher density of star forming galaxy, that what we expect. And this is the same idea for early type galaxy and late type galaxy. As you can see, the central part of the cluster, this zone here, are dominated by early type galaxy as we expected, and there are some influence that we have to investigate. I didn't discuss this in the paper, but we have to investigate well if this is the influence of the Hydra cluster. And the late type galaxy here occupy this zone here more, as you can see. So I will not read the table, but in general, what we can conclude this is that even with a not complete sample of galaxy, we can see the general behavior of cluster in the Antlia cluster as well. And when we have, I don't know, if you can use the photos to select more members, maybe we can see until we are completing the sample to investigate better the distribution of this type of galaxy, but we can reproduce well. And indeed, there is a work that has been done by Antlia, Giselle, Amanda, Rodrigo, that is looking at the Hydra supercluster that will involve the Antlia and the Hydra cluster. That I hope that it will come soon, this work, but the people is working on that. I will not read the summary and conclusion. I think that I presented it really quickly. This is a good thing, no? This is a good thing. I will not read the summary and conclusion, but basically is what we are doing. And I'm here working with Giselle Montego, because we are trying to investigate more clusters, not only the nearby cluster, but also other clusters. Thank you.
Thank you, Ciria. Very nice talk. We have time for questions.
Interesting talk. I have a very quick question. That is, in your sample, can you distinguish the star-forming galaxies with bars and without bars? And in the correlation, because you found no correlation mass size with the
the bulge and the
yeah.
Oh, sorry.
Can you discuss on this?
this is a really, okay, you are talking about this. If I can separate galaxies with bars or not bars. So this will be really interesting if you could do it. Indeed, I will come back more because I show in the beginning of the talk here, this galaxy has a bar, and we are not modeling the bar. We could do it because I'm using outfit M. That's a code that we can enter the profile, the Sérsic profile, the buccal exponential disk, and we can put a profile for a bar. But it's important to do this to fit well the components and get the information correctly, but I don't have like a catalog to know if the galaxy has a bar. What we could do, it's like training, I don't know, a machine learning code to look at the residue of the galaxy to see if the residue has some information as well of bar, and after that choose only galaxies to fit. I mean, to fit also, not a bulge, a disk, and a bar. And what will be interesting about this is that we will get the magnitudes of the bar. And we can see, photometry, of course, is not always so well, but we can try to derive, for example, the star formation of the bar. And see, we could look at, for example, if this relation that I show you, there is no relation between the size of the bulge and the size of the bulge and the mass of the galaxy. If there is something, maybe the galaxies that have bar are located differently in this plot. I don't remember, I think that was Ariana Cortese that asked me to look at, for example, I don't see any relation, but she told me to separate like bulge-dominated galaxy from disk-dominated galaxy. So maybe the bulge-dominated galaxies that are the pinky one, I don't know, magenta one, there is a relation between the size of the bulge and the mass of the galaxy, and the disk-dominated, there is no relation. Ariana, look at this plot, like, I don't know if you can see, like the blue ones. In general, it's flat, but it looks like the bulge-dominated galaxy, there is some relation. But in this moment, I'm doing the bulges. I need to do the bulges decomposition for more galaxy to have more information about it. Because in general, it's not so easy to separate the bulge and the disk. Antlia is not a cluster.
I'm not asking about Antlia. Nice talk, Ciria.
Thank you.
We just before your talk, we were discussing exactly this kind of plot, the relation between stellar mass or halo mass and the radius. And in models, if you fix the mass, the objects that are more compact, that is, have a smaller radius, have a larger star forming efficiency. Of course, you don't have access directly to this parameter in order to verify whether this is seen in your data. But with the spectroscopic observations that will come, you can use the proxies, for example, metallicity, because in principle there is a correlation between metallicity and efficiency, for example. So this is just a suggestion because there are many things written in this plot that we don't understand well yet.
Think alike, I agree.
Okay, more questions?
Because, yeah, of course I could expect that there is a correlation mass and size for star-forming galaxies exactly because of this argument that Laert gave. On the other hand, I'm not sure if we might expect to have a correlation like this with the bulge, because the bulge is, is the amount of stars that are that form in any class of galaxy. You end up with a bulge in the nuclear region due to it's unavoidable because you have a gravitational potential, so you have a profile. So we might expect, regardless of the mass and size relation, that the bulge is essentially of the same size and composition, etc. So I don't think there is much difference between the bulge, the bulge, not the and the galaxy mass
Yes.
and classification. So maybe it's okay,
Okay.
not finding a correlation, right? But it's a comment, of course.
Okay, it's a comment, and the truth is that I don't understand. I understand what you said, but as you can see here, sorry, we can have bush with a really high size and bush with a really small size. We have a variety of size of bush that is higher than the variety of size of disk in galaxy, but is not related with the mass. So this, it's like a little bit tricky. I understand what you said, but it's hard to understand. Because, okay, we have galaxies that evolve like a secular evolution far away from the cluster, and some moment it was accreted to the cluster. So probably this galaxy, the bush was formed really before, and I don't know. What I think that I was talking about this plot here, this plot here is that we can see that some galaxies that have a bush, have a disk, and lose material from the disk. It's like it starts to be bush dominated. The size of the bush is like the galaxy lose more size and disk, material in the disk, because the bush is as you said, the gravitational potential, it's really strong in the central part. I mean, the stars that are bounded to the bush continue in the galaxy. Indeed, I didn't talk here, but this is an important thing. We found in Hydra, for me, this is a high fraction of galaxy that have like a bush that's bluer than the disk. So in general, the bush of the galaxy, we can have star formation near the central part of the galaxy, but in general, the star formation, it is in the disk, in the star forming region. But in the cluster, we found that almost 40% of the galaxy, the bush is bluer than the bush is bluer than the disk. And probably it's like the galaxy, the high pressure strip, all those things remove the gas, but remove the gas for the outside part. And if the galaxy has a little bit of gas yet to form a star, it's bounded in the central region and they continue to form a star in the central region yet. So we can find this in the cluster. That is not necessarily we find this in the field galaxy, for example. This is one thing. But I don't understand very well why we have this behavior from the... I have to discuss more and then to understand.
Hi. Are you in foremost?
Yes.
Okay. And when you say the central regions, how many parsecs are we talking about, more or less?
The central region, you are asking about the size?
Yeah, for example, you said maybe there are some bulges with some star formation because some gas stay in the central region. So when you're seeing central regions, more or less, so is what?
Okay.
In terms of kiloparsec,
when
more or
I'm
less.
talking, okay, I understand now. When I'm talking here, I model the galaxy. I will answer your question. When I'm talking here, I'm talking about really nearby galaxy that we can separate the bulge and the disk. There are some galaxies that we cannot do it because high redshift or low resolution of the images. This will change. In this plot here, I'm putting the information about the size of the, but this is log. The size of the bulge and the disk in kiloparsec, for example. But I understand your question because you asked me about formos. If I'm not mistaken, formos, the fiber will be like 3 arcseconds. 1.5? 1.5? It's like deci. Okay. So 1.5. For some galaxy, we don't have information from the disk. For the really nearby, probably for the really nearby galaxy, we have information only for the bulge of the galaxy. And maybe, I don't know if you will be able to see the star form, for example, for galaxy to have some star forming region nearby to the bulge, maybe we'll not be able to see, but I don't know. For the galaxy, for the cluster that with a higher redshift, we will have like the information from these two parts. But for really nearby, like Antlia, Hydra, probably we have only the really central part of the cluster. Oh, sorry, of the galaxy. And maybe we'll not be able to see this.
Yeah, it would be interesting to know if you will be able to see this. Because
yes. Yes.
Because you said you were preparing the catalogs, right? And
Yes,
you have
I prepared the targets catalog.
yeah.
We use it basically for almost all the cluster. We use photos information. We use the photos to select the galaxies that have photos nearby to the cluster, up to 5 out of 100. But we didn't select the galaxy by size, only by the photos. So we have a range of size of galaxies, a range of different morphology of galaxies. Except if the photos has a precision related to the type of galaxy, I don't know. The physical properties, yes, of course. We know that the galaxy with emission lines, if the galaxy is nearby, probably the photos is more precise, but not by shape of galaxy. That's what I'm interested to see, to separate the bulge and the disk. But we can use the color as a proxy as well. Even if you don't have the spectroscopy, we can use the color to see if the bulge or the disk are more star forming. But to do this, we need the spectrum of the galaxy.
Okay. More questions? No? Thank you again, Ciria.
Thank you.